I think I saw something about gravitational waves in the notes too. Does SQS predict anything different there?
Yes, it does. Very interestingly, SQS predicts the existence of something called entanglement echoes from merging black holes.
Entanglement echoes.
Yeah. These would be subtle modulations, like ripples on the main gravitational wave signal, appearing after the main merger event. The prediction is for an amplitude modulation around delta asim 10.5, maybe in a frequency range that future detectors like LISA could pick up.
And how's that different from standard general relativity?
Standard GR predicts the gravitational waves to smoothly fade away after the merger, what's called the ring down. These echoes would be an extra signal, a kind of reverberation linked to the entanglement structure. Detecting them would be a pretty significant piece of evidence for SQS.
That gives us a really specific thing to look for with the next generation of detectors. Fascinating. It seems SQS connects to so many different areas. How does it stack up conceptually against other big theories trying to do similar things, like string theory, for example?
That's a really important question, putting it in context. So let's take string theory and maybe another one like mere three-time dark matter. In terms of unification, SQS, as we said, tries to unify gravity and quantum mechanics, plus explain the dark sector, all under this one gauge symmetry.
Okay.
Mere three-time dark matter is quite different. It proposes extra time dimensions and a sort of mirror universe interacting gravitationally. String theory, of course, suggests everything is made of tiny vibrating strings in usually 10 dimensions, and that different vibrations correspond to different particles and forces.
And their explanations for dark matter are totally different too, right?
Completely. SQS says dark matter is emergent entanglement. Mirror three times suggests mirror particles. String theory often points towards hypothetical supersymmetric particles, or WIMPs, although finding those is proven difficult.
And what about testability? That seems like the crucial point for actually figuring out which, if any, of these ideas is right.
Testability is absolutely key. SQS, as we've discussed, offers several potential tests. The entanglement echoes in gravitational waves, the specific dark matter halo profiles, the spectral lag from gamma ray bursts. These are, potentially observable things.
Things we could actually measure, maybe soon.
Potentially, yes. Mirror three-time dark matter also has predictions like maybe weird gravitational lensing patterns or missing energy in particle colliders. String theory. Well, if predictions often involve incredibly high energies, far beyond current experiments, making direct tests very, very challenging. Though it does have implications for things like black hole physics or cosmology that might leave indirect clues.
So SQS seems to have more near-term observational handles.
It appears that way, yes. And it's worth noting some of the very recent data from 2023, 2024, particularly JWST, finding those early massive galaxies, and maybe the tentative spectral lag hints from Fermi LOT. They seem to, let's say, align reasonably well with what SQS might expect, perhaps more readily than some other models.
Interesting. It sounds like SQS is offering a compelling, maybe even simpler conceptual framework for these big mysteries, especially compared to the sheer mathematical complexity of something like string theory. But what's the current observational status? Where does the evidence stand right now?
Okay, so as mentioned, the JWST results on early massive galaxies are intriguing. They don't prove SQS, but they fit nicely with the idea of early entanglement hubs' seeding structure. That's supportive.
Okay.
For gravitational waves, the current LIGO Virgo detectors haven't seen entanglement echoes yet. But their sensitivity might just not be quite there, especially for the predicted frequencies. Future detectors like LISA or upgrades to current ones will be crucial.
So watch this space, basically.
Exactly. And the spectral lag from Fermi LAC, it's tantalizing, but it's statistically limited. We need more data, maybe from other instruments, to really confirm if it's a real effect consistent with SQS's prediction of non-commutative spacetime.
So we have some exciting hints, some potential alignments, but definitely not conclusive proof yet. Lots more work needed.
Absolutely. And there are major challenges. One huge hurdle for SQS and any quantum gravity theory is just the sheer difficulty of doing direct experiments at the Planck scale. It's almost unimaginably small.
Right.
Also, to really nail down the dark energy prediction in SQS, we need incredibly precise measurements of the universe's expansion history and large-scale structure. This means pinning down how the vacuum entanglement entropy evolves, which requires data from next-generation surveys like DSI or the Euclid Space Telescope.
These are definitely monumental tasks, trying to probe both the infinitesimally small and the cosmically vast. It really highlights the ingenuity involved in even developing these theories. Okay, let's shift gears slightly. Beyond the physics and observations, what are the broader, maybe even philosophical implications if SQS turns out to be right?
Now we get into some really deep territory. SQS paints a picture that could fundamentally change how we see reality. One major implication is this idea of reality as computation.
Reality is computation.
Yeah. The framework suggests the universe is constantly processing information and optimizing its entanglement, almost like it's running a program, like a giant self-organizing quantum neural network learning and evolving.
The universe as a giant quantum computer, optimizing itself. Wow, that's a big thought.
It is. And it touches on really fundamental questions, like the old free will versus determinism debate.
Oh, so?
Well, the entanglement-driven dynamics suggest an overall drive towards global optimization, which sounds deterministic. But quantum mechanics, which underlies SQS, still has inherent randomness and uncertainty at the local level. So you might have this global goal, but with local indeterminacy playing out along the way.
So, a kind of cosmic destiny driven by entanglement, but maybe with wiggle room for chance or something else. At the quantum level, that's a really complex picture.
It is. It doesn't provide easy answers, but it offers a new lens to view those classic questions.
Okay, now let's really speculate. Let's push the boat out. If SQS is correct, and we eventually figure out how to harness its principles, what kind of revolutionary technologies might become possible? Things that sound like science fiction now.
Right. This is where the potential is truly mind-blowing.
Yeah.
If we could understand and manipulate the entanglement structure of space-time itself, well, consider quantum gravity engineering.
Quantum gravity engineering.
Okay, for example, it's theoretically conceivable within SQS that you might be able to stabilize wormholes. You could potentially manipulate the entanglement entropy gradients in specific ways to keep a wormhole open for, say, faster than light travel. The math, delta T plus 2 hints at this possibility.
Wait, seriously, stabilizing wormholes for interstellar travel, that's straight out of sci-fi.
It is highly speculative, of course, but the theory might allow for it. Or think about energy. SQS suggests the vacuum itself has entanglement energy fluctuations. Could we harvest the zero-point energy?
Energy from empty space.
Potentially. The raw power density, something like P-sim frac P2, looks tiny on large scales because of the Planck length squared. But maybe at the nanoscale, or if we found clever ways to tap into it, it could be a virtually limitless clean energy source.
Unlimited clean energy. That would change everything. What about communication?
Well, the non-local nature of entanglement inherent in SQS raises the possibility of entanglement-based communication. Using these quantum holographic channels, maybe even faster than light signaling could be possible.
FTL communication.
Again, hugely challenging. Decoherence, the tendency for quantum states to collapse, especially due to gravity, would be a massive hurdle. But the theoretical possibility might be there.
Wow. Faster travel, unlimited energy, instant communication across space.
Yeah.
And what about understanding the cosmos itself?
SQS could lead to what you might call predictive cosmology. Instead of putting dark matter and dark energy into our models by hand, we could potentially simulate the universe's evolution from first principles using SQS, perhaps with quantum tensor networks that embody this symmetry. DM and DE would just emerge naturally as outputs.
Simulating the universe from the ground up. Incredible. Any applications closer to home? Medicine, maybe?
That's also conceivable. Think about entanglement healing. If biological processes have quantum aspects linked to entanglement, maybe we could manipulate cellular quantum states to repair damage, counteract aging, fight disease in new ways.
Healing by reprogramming quantum states.
Or even neuroholography. If consciousness has roots in the brain's interaction with the quantum network of space-time, could we interface with that network directly? Enhance cognition. It's very speculative, but SQS opens doors to thinking about these things.
Boosting brain power by plugging into the fabric of reality. These are truly paradigm-shifting ideas, and maybe new ways to just see the universe.
Exactly. We might develop space-time sensors. Using ultra-precise quantum interferometry, perhaps we could directly detect the Planck scale graininess SQS predicts, or even see dark matter through its subtle influence on the background entanglement field.
It's just amazing to think how one fundamental shift in understanding could ripple out into so many transformative possibilities.
It really underscores the power of fundamental physics.
Well, this has been an absolutely mind-opening deep dive into the concepts, the core ideas of symmetric quantum spacetime. To try and wrap it up, the central theme seems to be that the universe isn't just particles moving through a fixed stage of space and time.
Right. It's more like a dynamic, self-organizing quantum system where entanglement and this deep underlying symmetry are the truly fundamental players.